Okay, so this week's knowledge share is on batteries. So there's two types of batteries, secondary and primary. Primary batteries refer to batteries that can only be discharged once and can't be recharged after. So they're not used very commonly. The most common secondary type battery is lithium ion. So those would be the batteries that are in cell phones, laptops, pretty much everything. Lithium polymer batteries are similar, but they just have a higher power density. So there's more watts of power per kilogram. Nickel metal hydride is an older technology that you'll still see fairly commonly, and then nickel cadmium is used in old power tools, and it has a memory effect where if you don't discharge it completely before recharging it, then it'll have a lower capacity in the future. So there's no single battery that we can just buy and put in the car to power it. So we actually have to make we have to connect the cells in different ways to get the proper power that we need. So you can either connect them in series, where it is shown in this diagram here, where the negative terminal goes to the positive terminal of another battery. And this will increase the voltage that at the output. So battery cells are voltage, they can be treated as voltage sources. So each, like in this diagram, there's 3.6 volts across this battery cell. And then the top battery cell has another 3.6 volts across it, but that's like the ground is at the top of the previous cell. So the total voltage across those two is 7.2 volts. And then the current through them will be the same because of Kirchhoff's current law. So there's just nowhere else for the current to go. So it has to just go through both the cells and it'll be equal at all points in this loop. And then cells that are connected this way are called a string. So the other option is that you can have cells connected in parallel. And when they're connected in parallel, the current, so in each cell, you could be drawing 1 amp, for example, in this diagram. And then at the load, you'll basically see 2 amps because the current sums together. But the voltage across them will only be 3.6 volts. If there was like a difference in voltage before putting the cells into the circuit, so if one was at 3.7 volts and one was at 3.5 volts, then they would quickly like balance the charge between the cells. So you'd have current flowing from the higher cell to the lower cell. And then cells that are put in parallel are called a module. So like I said before, we need to combine cells in series and parallel to make a battery pack that's large enough for our purpose. The trade-off here is that there's extra weight to carry around because the cells weigh a lot, at least when you have as many as we do. So then when you're building the battery pack, you have to consider like how many cells do you need in series and how many do you need in parallel, and how big your battery pack should be in total. So this is the size of the battery pack is based on how much energy you want to store. So I guess our strategy team can tell us like how much energy is like an optimal value that we need, and then we can build a battery pack that has that can contain that much energy. The series connections is based on the operating voltage that you are aiming for. So our motor controllers, I believe, are the limiting factor there. So our battery pack is about 150 volts when it's fully charged. And this is, I believe, I can't remember the exact value, but our motor controllers have a limit that's slightly higher than that. So that's why we can't have any more cells in series. Then basically the parallel combination is based on what we expect our maximum current draw to be. And the maximum current draw will be mostly from the motors. And then also when we're charging, that can be based on like either regenerative charging from the motors or the solar array or just charging from an outlet. And then there's also scoring requirements for competition, but I believe this only applies to single occupant vehicles.
You do get penalized based on how much energy you start with. So that goes into the energy requirement.
Okay. So for measuring the cell energy, there's a couple different ways that it can be expressed. So usually you'd look at the data sheet to find this information. So capacity refers to the amount of charge that a battery can hold. So capacity will sometimes be expressed in terms of amp hours or watt hours. And this refers to if you were drawing 1 amp, or the number of amps that you could draw and discharge it in 1 hour, or same thing with watts. And then there's also the C rating. So this refers to the number of times you can discharge it in an hour. So if you have a C rating of 1C, then you can discharge the battery. You're drawing a current that would discharge the battery 1 time in a full hour. So if you multiply the C rating by the capacity in amp hours, then you'll get the maximum discharge current that you can draw from that cell. And then often you have to actually measure this yourself, because sometimes in data sheets it's exaggerated or not entirely accurate.
That's more for in data sheets. It's usually pretty good, but like batteries that you buy from China or on eBay, often just go for the highest capacity and highest C rating they can and just put it on the listing because people will buy it. So we buy our batteries from reputable sources. We get them from LG to avoid any kind of falsified information. This section's for the 18650 cell construction. So I'm going to go to the next slide, Liam. First off, why 18650s and what are 18650s? Basically, it's just a cylindrical battery type that's 18 millimeters in diameter and 65 millimeters long. It's pretty much just as standard as a AA battery is, except in different circles. AAs are obviously much more available in home use. 18650s are very common in pretty much any other high power electronics use. So RC cars are a good example of that. You can find them everywhere. Lots of online shops will sell them. They're pretty commonly used in vaping as well. But yeah, typically the newest chemistries are put inside 18650s because they're easy to manufacture. It's just one roll of a material that gets rolled up and stuffed inside, and then you have your 2 terminals on either end. So it's super simple to do. For the newest battery chemistries, such as solid-state batteries, this is transitioning a little more into pouch cells, so it's no longer prismatic or no longer cylindrical cells, but like a flat prism. But for now, the ones that are readily available and commercially viable, the best ones available are in the 18650 style. So I'm going to go on the next slide. So this kind of shows what is an 18650 cell and how it's connected. So there's 2 terminals, obviously the positive and the negative. And as you can see in the diagram here, the negative terminal goes all the way around the outside of the battery and loops around to the edges of the top. And the positive tab is just that little silver part in the middle. It's usually made of nickel or aluminum. The casing is steel. That top tab is usually nickel or aluminum. But because that negative can wraps all the way around to the top near the positive end, we have to be careful for what's called shoulder shorts. And you can see a picture of one in the bottom right. Basically, as they're assembling this battery pack, they punctured the insulation on the top of the negative terminal, and they connected it to the positive terminal with that little bus bar there, and that shorted the battery and caused it to burn. So we obviously want to avoid that, so we have to design our battery pack to protect that area. The insulation is usually a PVC heat shrink. It's the green on the outside you can see there. That's just to protect the negative cell can, to protect any accidental touching of live electric terminals. As in the diagram with all the series cells earlier, the negative cell can, if it's at the top string of a battery pack, that can be in our pack, that'll be at about 145 volts. So we want to protect the negative cell cans, and it comes manufactured with those casings on it. So that's all good. And there's the insulating washer, is a little white part around the ring there. So I just add a little more protection to the negative on the top to avoid shoulder shorts. So inside an 18650 cell, you'll see those rolls of cathode and anode that were mentioned earlier. It's just the positive electrode, the negative electrode, and then a separator in between them. Separator is typically a super thin piece of plastic, and it's just wrapped up in a roll and stuffed inside the cell. And then there's a few other features on it that are near the top. There's a CID and a release vent and a PTC. The CID is a current interrupt device. If you go to the next slides, there'll be a few more pictures of that. Okay, so let's start with the PTCs. PTC stands for positive temperature coefficient. One of the important things with batteries is that you want to keep the operating temperature low enough that it doesn't cause an explosion or a thermal runaway. And we'll get into that a bit later. But this is one of the ways that manufacturers help prevent that. It's not the best way. Basically, as the temperature of the battery increases, the resistance will increase. And because the resistance increases, the current decreases. And since the current decreases, then you get less heat production. So the battery will stop heating up. That's the idea. In the diagram here, you can see that the phase transition happens over 100 degrees Celsius, around 130 degrees. And that's when the material really starts to gain resistance and make a significant effect on the current. So up until then, it doesn't really make a difference. But for some batteries, and in some conditions, 130 degrees is still enough to initiate thermal runaway. So it's not to be relied upon, and there should definitely be other methods of protecting for overtemperature events. Let's go to the next slide. The CID stands for a current interrupt device. And you can see it's a little tab there in the middle of the positive terminal. And that connects to the positive side of the jelly roll of the cathode and anode. It connects that to the positive terminal of the battery cell. And what happens when there's enough pressure that builds up inside the cell, pressure can build up because of if the cell is too hot or if you're trying to charge or discharge it too quickly, then pressure will build up. And if that pressure buildup is too much, that little vent there will open up and it will pop the CID, we say. And that will stop the current path between the jelly roll and the positive terminal of the cell. So that's another method, but typically the pressure is still like way higher than is comfortable before this pops. It can be useful in some situations, but again, we don't want to rely on it because there are bad things can happen to the cells before this will trip. So into the thermal parts of the batteries. As we mentioned before, there is thermal runaway. If you want to the next slide. And we'll go through the basics of that. Cells produce heat. Looks like I forgot to add an image in there, but I think that comes up later. The cells produce heat because of a simple equation: power equals current squared times resistance. And that heat has to be dissipated. It just sits in the cell, and the cell will heat up. And until we need to provide a way for it to escape, or else just keep heating up the cell, and the cell will get too hot and go into thermal runaway. The other source of the cell of heat is chemical reactions inside the cell. I believe the reactions that create the current flow and electron flow are actually slightly exothermic, but typically that's insignificant, and the internal resistance causes a much higher heat than the chemical reactions, so we use the internal resistance to model the heat. So thermal runaway happens when there's an exothermic reaction inside the cell that will keep propelling itself to continue. And a few causes of that are internal shorts. So if there's a short between the cathode and the anode inside the cell, that'll create a high current, low resistance path, which will create a lot of heat inside the cell, and it'll just shoot up. And once it reaches a a certain temperature, then the reaction will just keep on going. It just burns its own contents, and there's no way to stop it. Another way that it initiates is by just letting the cells heat up too much. If you have really high operating temperatures, then you'll be closer to that limit of initiating the thermal runaway. And because it is a chemical reaction that happens, you may have heard of a few of the terms such as activation energy. Basically, all chemical reactions need a certain amount of energy in order to proceed. And as you heat materials up, they have more energy. So the hotter the cell is, the closer it is to the activation energy required to start thermal runaway. So we want to stay well within the data sheet recommendations for operating temperature. For us, we need to keep it under 60 degrees Celsius for the data sheet for the cells that we're using. And the TR propagation, or thermal runaway propagation, is pretty scary. Basically, that's when one cell goes into thermal runaway, and then that cell, as it heats up and as it, the graph there shows almost 600, 700 degrees Celsius, that will heat up adjacent cells and trigger them into thermal runaway as well, which is obviously not a good thing to happen, because then you have cells exploding one after the other. So you go to the next slide. And when cells explode, you'll hear one cell basically pop its CID and then explode out the top, and then another one and another one and another one. So we don't want that. There were some cars in the World Solar Challenge that had this happen, and there was basically nothing left of the car. So we want to be very careful with our thermals. These are some pictures of the thermal camera of some of the testing that we've done. The one on the right just shows basically batteries do heat up. They're about 42 degrees there. And that test was just with the nominal current draw that the data sheet suggests. So that indicated that we do have to look into cooling and make sure that we're adequately cooling the cells. And on the left there's temperature distribution within the pack. So the cells on the outside were a little bit cooler than the cells on the inside were. So with that data, we decided to make some change in the modules and allow for some more airflow into the middle section of the battery pack. Go on the next slide. Cell cooling, there's typically a few ways that it's done. Water cooling, forced air cooling, or conduction cooling. Well, I guess these are all conduction cooling. But water cooling is you just put basically a radiator through the cells. You have typically a copper pipe with a large contact surface to the cells, and that'll transfer heat from the cells to the water, and then you pump that water through a radiator and blow air across the radiator to cool it down. That's pretty expensive and comes with lots of risks, especially since you're putting water near high voltage electronics. It's hard to do right, but when it's done right, it's really effective. But because of that initial investment, then it takes a lot of time, and with our build timelines, we're not able to pursue that option. Forced air cooling is the easiest way. Just put some fans in there and blow some air across it. That's what we're doing for our pack, and it's not quite as effective as water cooling, as that just means we need to pay a little more attention to testing and validation when we're doing that. And then conduction cooling, I'm not sure that's the right word for it, but another way is just to add a large thermal mass to the cells, so that the heat from the cells can be sunk into something else. Maybe just put a heat sink on top of it, and that will absorb all the heat from the cells. So there are some materials that do that pretty effectively. You just pop the cells in this something like a phase change material that will absorb all the energy from the cells as they heat up. But those are pretty new methods, and yeah, we don't have access to those, unfortunately. And yeah, the requirements are defined by the data sheet, so we have that 60-degree maximum. So yeah, mechanically, there's a few different levels of the pack: the cell, which is the smallest unit of energy; the module. In our case, we have 50 cells in each module, and then the pack, which has all the energy storage in the car. Our pack is about 11 kilowatt hours, and there's 900 cells total. And the reason we split it up into multiple modules instead of just making it one large chunk of batteries is because if there are failures, if there are cells that aren't performing as good as other cells, then we want to be able to swap them out. And we don't want to replace 900 batteries when we do that, because that's it's pretty expensive. So we split them up into smaller sections to remove them and replace as needed. Yeah, so as Leah mentioned earlier, cells can be modeled as a constant voltage source, but that's not entirely true. It's a very good model for determining electrical characteristics, but when you want to determine how much energy they store, you need to look at the full picture. So basically, as cells discharge, their voltage will drop, and that's because the concentration of ions in the electrodes drops. And there are some equations that you may or may not have gone over in chemistry, but those basically show that the electrochemical potential, the cell voltage, is proportional to the concentration of those ions. So as you discharge it, the voltage will drop. And that the curve that you see there is characteristic of a typical lithium-ion cell. And there are different C ratings for the discharge currents. As you can see, the faster you discharge it, so higher current, the lower the voltage will be. And that's because of an internal resistance inside the cell. Cells are not a perfect voltage source. There's always going to be a voltage source and then a resistor in series with it. And that's one of the important characteristics that we need to measure of the cells to ensure that they're healthy cells and they're safe to use. Because that's the resistor that will determine how much heat the cell produces and how likely it is to go into thermal runaway. Yeah, and when to keep in mind when you're building packs, the voltage limits are not fixed. The voltages are not fixed. So you'll have a swing from 2.5 to 4.2 volts on a single cell. When you have 36 cells in series like we do, your voltage swing is now 90 to 150 volts. So you need to ensure that all the equipment you're operating is able to work with those voltages. And those voltages are typically given in the data sheets. The limits are somewhat arbitrarily defined, I think, but there are reasons to not go above them. Basically, as you charge it more, you're stuffing more ions into the crystal structure of the cathodes and anodes, and that will increase the pressure, which will increase the likelihood of thermal runaway. As you discharge it more, there's more of a tendency to there's what's called dendrites, and it's basically a crystal structure that will form, and the ions will form like a spike that will poke through the separator and cause an internal short, which is again more likely to cause thermal runaway. So we like to obey the data sheet. The manufacturers typically know what they're doing. So our limits are 2.5 volts discharged and 4.2 volts for fully charged.
Okay, so I'm just going to quickly talk about how we actually measure our battery pack and keep it within safe limits. So our BMS system has 3 different boards in it. The first one is the BMS carrier board. So it's responsible for communication. So it has a controller board on it. So that communicates with the rest of the car over the CAN network. And then it also communicates to the other board through ISOSPI. ISOSPI is a differential communication protocol that can be converted between SPI and ISOSPI. So it's really useful for communicating to other ICs, and because it's a differential signal, it has a high immunity to noise. The main computation is done on our controller board, and then there's also a Raspberry Pi that sits on the left side that can do any computation that we I guess any strategy modeling things that we don't want to do on the controller board. The controller board also, this basically just measures the parameters of the battery pack, so the voltage and current and everything. And then the controller board and firmware has a comparison that determines whether it's within safe operating limits or not. The BMS carrier board also controls the main relays, so that's these two connectors in the middle. It can turn them on or off, and then there's these connectors on the right side are responsible for the fans, so it can change the speed of the fans or turn them on and off as well. And then the BMS carrier board also detects when the kill switch has been pressed, so we need the car to shut off and throw like a BPS fault when that happens. So one of the other boards is the current sense board, and it's very simple. All it does is sense the current. Basically, it gets 12 volts from the BMS carrier board, and then that's isolated because it actually sits like at the top of the battery pack. So its ground is actually at the top voltage of the battery pack, so it could be as high as 150 volts. And then it has this, I guess, bronze-looking thing here is the shunt resistor. So it measures the voltage across the resistor and then amplifies that, sends it to an ADC, and then that data is communicated back to the BMS carrier through ISOSPI. And then the analog front ends are the boards we use to sense the voltage and temperature of the battery pack. And we have 3 of these in our battery pack right now. They're also responsible for balancing the cells. So this just makes sure that all the cells have the same voltage, and this evens out the load experienced by each cell, and also can increase the maximum energy that you can use from the pack. And so yeah, it has an IC that does like all the measurements and some filtering, and then communicates that back to the BMS carrier through ISOSPI. And these boards are connected through like a daisy chain, so that we can communicate with all of them without needing addressing. And that, yeah, I guess then like we use thermistors to measure the temperature in the battery pack. So then these are multiplexed through this IC. So this just allows us to measure more thermistors without needing like a ADC for each one, or like a pin on the IC for each one. And that's everything in our battery management system.
Any questions?
Yeah, well, that was a bit of a shorter knowledge share, but good job, guys. We also have a strategy meeting to talk about what strategy has been up to. I suggest all of you try to attend. I think it's a general meeting, but it should be in the strategy channel. Yeah, we'll upload the video and the slides for this on the Confluence page. Okay, thanks everyone.
Yeah, the strategy will be super interesting. Definitely join it.